This video investigates the idea of negative mass in the weak field limit of general relativity, where the equations of Newton are a good approximation for describing motion in weak gravitational fields. It shows how the equivalence principle of general relativity leads to some non-intuitive consequences for the interaction of positive and negative masses. Now, negative mass has never been observed, but if it did exist, what might happen? Well, it turns out the mathematics of general relativity can handle negative mass. So let's start, say, with the line element for the Schwarzschild geometry, which was derived under the requirements that it be independent of time, invariant under time translation, so it's static, asymptotically flat, and here's our line element. Now, these conditions are still met if capital M here is replaced with minus m. It's still independent of time, still invariant under time translation, still asymptotically flat. All right, now let's just say we have a particle of mass m subscript 0 and it's released from rest on a radially and allowed to fall radially inwards on a path towards a mass m, Schwarzschild mass m. Its equation of motion is given by this equation here, which I've produced in a separate video on the Schwarzschild, one of the videos on the Schwarzschild geometry series, and that equation there. Now, notice this motion is not affected by the algebraic sign of m0 because this quantity is squared. So whether it's positive or negative doesn't affect the equation. Now, the equation of motion of a particle with mass m0 and moving in the equatorial plane in the Schwarzschild geometry, again in a separate video, we found this result here. But again, the mass of this particle is squared, so whether it's positive or negative, it doesn't make a difference. Now, this motion is independent of the sign of the mass, the algebraic sign of the mass of the particle due to the squared term, these squared terms here. All right, next bit. Now, far from the source mass, the Schwarzschild geometry approaches that of flat Minkowski space-time, asymptotically approaches it. In this region, the field is weak, and if we also consider the slow speed case, then the laws of Newton are a very good approximation for describing motion. So in this region, the metric can be seen as a small perturbation to the metric of Minkowski space-time in the form here. So if we look at the 0,0 component, the time component of the metric here, G00, then we look at it as being made up of the time component, eta 00 of the Minkowski flat space metric, plus this perturbation, small perturbation, H00. There's a whole video that I've done on the weak field case in general relativity, and this is just a brief, I pulled out a few lines here just as a brief summary to justify what I'm doing in the video here. All right, so we found this, and we could say a suitable Newtonian potential would be this object here for the mass at the center of the Schwarzschild geometry and the mass, little mass m that we're allowing to fall in on some radial path. Right. We found that the Christoffel symbol of the second kind that was non-zero was this one. I is the Latin index I here, referring to the spatial indices, not the time one, just the spatial x, y, and z components, if you like. And 00 here, this was the only non-zero Christoffel symbol of the second kind, and we found it to be this object here. We worked it through and got this. Remember, for each of the spatial indices, eta II is 1. Next bit here, we went then to the geodesic equation and substituted in what we knew here. Tau is the proper time of the particle falling inwards, and produce this object over here. And for all these details, please go see that video. I'm just briefly reminding you of it here, set to 0. We then solved that for the proper acceleration of the particle, and we found it to be this object here, the differential operator nabla here of the small perturbation, and substituting on here, we found this, and a very familiar form here from Newtonian dynamics. So in the weak field slow speed case, Newton's laws are a valid approximation to general relativity and are suitable to deal with questions of general relativity. In the weak field low speed case, we can use Newtonian laws. All right, there are two types of mass to consider: the inertial mass, and this is the mass as in Newton's second law, F equals ma, the mass m here, inertial mass; gravitational mass, as in the mass in Newton's law of gravity, or Newton's law of gravitation, F equals this object here. In Newtonian dynamics, though, there is no requirement for inertial or gravitational mass to be the same. That it works out that way is purely coincidental and very fortunate. All right, now in this video series here, we're going to have a coordinate system here. We're going to have a mass m1 and a mass m2, positive or negative, or both are going to be positive or negative. We're going to have all motion to the right will be positive. That's the positive direction there. And you'll see shortly in the diagrams where more details added. All right, now general relativity begins with the equivalence principle, which says that inertial mass and gravitational mass are identical. And that's not required in Newtonian mechanics, but certainly it is in general relativity. The equivalence principle is a starting point of general relativity, and it says that inertial mass and gravitational mass are identical. So negative mass in Newtonian dynamics, so you have a mass m2 of negative value, the net force acting on it would be m2 times A equals g m1 times minus m2. Remember, m2 negative, gravitational mass m, we're talking about gravitational mass, negative. It would be, because gravitational mass involves attraction, we have to take care of the sign with that. And so the net force would be this. Now, but in GR, the same equation, in general relativity, the same equation must be minus m2 times A is this object here. All right, so I want to stress on that. We'll see what consequences that has as we go along. All right, so let's start with two positive masses, and this analysis will be valid in both Newtonian dynamics and general relativity. This is where they agree with each other, because fortuitously inertial mass and gravitational mass will be identical in both cases. So you have at coordinate x1, you have the first mass m1, at coordinate x2, you have another mass m2. Motion to the right will be taken as being in the positive direction. All right, the equation of the motion are m1 d2x1, that's the acceleration on the first particle, is equal to this object here, all very familiar. m2, this, notice the minus sign here because this particle will be moving to the left. This particle will accelerate to the right, attracted by this particle m2. This particle m2 will be attracted to the left, hence the negative. All right, so it will move in the negative direction, hence the negative there. Now, divide through by m1 here, divide through by m2 here, and the accelerations of the respective particles. For the first one is this, for the second one is that. No surprise, the second one's accelerating to the left, and we've defined motion to the left as negative. Add the two together, and we get 0, because the net acceleration, if m2 equals m1 that is, the net acceleration is in towards the center here. So the sum of the acceleration is 0. Or the acceleration of the center of mass is 0. Or in other words, rearrange that, the acceleration of particle 2 is the negative of the acceleration of particle 1, given they're the same mass. All right, now the acceleration of m2 with respect to m1 is this object here, and that's the difference between the two, and that's for particle 2 it's minus this, for minus, and then for particle 1 it's this object here. This is going to be a useful quantity here, which is why I'm after this one. I'll just go into that now. So here's the net acceleration, adding them together. Sorry, taking the difference of them. And we're going to set the difference in the coordinates x2 and x1, give that the value r. And when we do that, set that, we can take that out. x2 minus x1, we're going to set that equal to r. We get d2r dt squared. And for the right-hand side here, this x2 minus x1, the absolute value of it all squared is r squared. And so what we have now is the equation describing the acceleration of the system, d2r dt squared is minus g m1 plus m2 on r squared. And net acceleration is inwards, hence the minus. All right, now, when I say net acceleration is in, we know the two particles are going to move closer together, so r will decrease. And the acceleration of that decrease is this object here. Now, a first antiderivative of this can be shown to be the expressions in the parentheses below. And the reason for deriving these first derivatives is that they'll give us a very interesting condition which will help us analyse this motion. Now, what I'm going to show is that the derivative, the ordinary derivative with respect to time of this object is equal to the ordinary derivative with respect to time of this object here. So what's in the parentheses here on both sides is a first derivative of that equation we saw earlier, which is this one down the bottom. Well, let's establish that's the case. So work it through. d dt of this object here is 2 dr dt times this object. d dt of all this minus 2g, all of that, and use a chain rule again here as we did on the left. That becomes negative 2 dr dt. Takes a negative out front here, plus d alpha. Alpha was a constant. Alpha was a constant of integration, and so the derivative, ordinary derivative of that will disappear to give us 0. And over here, this dr dt will cancel with this one. This 2 will cancel with that one, and we're left with d2 r dt squared is negative this object here, just like we expected. All right, so the material in the parentheses here is a suitable first antiderivative of this second order differential equation. All right, let's just come back to our situation now. At t equals 0, we're going to set the distance between m1 and m2 at that instant in time as big R, capital R. And then we're going to analyze what happens to that distance over time. m1 is situated at position coordinate x1 and m2 at position coordinate x2. And we found that our first antiderivative is this object here plus some constant. Now, at t equals 0, dr dt is 0 at that instant in time, and little r is equal to big R at that moment in time. So let's substitute that in there. This is 0, and so 0 equals all of this plus alpha. Rearrange to get alpha, we get minus this object here. And next slide over, we'll substitute our alpha in over here. So that dr dt all squared is this object. Tidy it up, factorise out the common numerator here. Take that front, 2g m1 plus m2 times, in brackets, 1 on little r minus 1 on big R. And when we tidy all that up, this is what we've got. Here's our first derivative, first integral, if you like. All right, now, dr dt all squared must be greater than 0. There's no question about that. That's a positive quantity. And given that so if this is a positive quantity, and given that 2g and then in brackets m1 plus m2 is clearly a positive quantity, then the only thing we need to worry about is what happens to 1 on little r minus 1 on big R. That has to be equal to or greater than 0, because the left-hand side is equal to or greater than 0. And so when we add 1 on big R to both sides, we get this object here. When we solve it, we find that r is equal to less than big R. So once the particles start initially at distance of big R apart, as time goes on, that distance decreases. Its final distance at any point in time will be equal to or less than big R. So this result tells us the distance between the two particles always decreases, and so we have attraction. That's Newton's law, Newton's law of gravity, and that tells us that between two masses you have a force of attraction. Now, in the weak field case, in general relativity, that is still valid. That's still the case, as we see in our solar system and elsewhere. All right, next bit. One positive and one negative mass. So here at x, the coordinate position x1, we have positive mass m1, coordinate position x2, we have negative mass, m2. And at t equals 0, the distance between them is big R. Motion to the right is in the positive direction. And let's analyze what happens here. All right, now we set up the equations of motion. So the net force on M1 is this object here, and in terms of Newton's law of gravity, it gives us this expression here. For M2, notice we must have the negative on the left here, and obviously on the right here, and we have negative in front. We expect attraction between the two. So the acceleration of the first particle, acceleration of the second, both these objects here, add them together, and we get this object here, telling us that the center of mass, the whole system, is accelerating to the left. We'll look at what that means shortly. Let's go for the difference again, because we want to analyze that difference between x2 and x1. What happens to that to show, is there attraction, repulsion, or neither? Anyway, so substitute that, minus this one, minus this one here. When we get that, it produces this object here. All right, so replacing x2 minus x1 with r, again, we have this object here. Again, we'll show that the material in the parentheses here on both sides is a suitable first antiderivative, but we'll differentiate both sides to bring us back to this. Doing that, chain rule here, chain rule over here, constant here, disappears, cancel out dr dt on both sides, and we're left to cancel out the 2's on both sides, and then we're left with d2r dt squared is this object here, which is what we started with. So clearly our first suitable antiderivative here, dr dt all squared, is minus all of this plus a constant. All right, all we need to do now is find the constant at t equals 0. dr dt is 0 at that instant in time, and little r is equal to big R, as we saw in the diagram earlier. When we do that, we set 0 on the left here, dr dt is 0, so that 0 here is equal to this plus alpha. Rearranging, we get alpha as the plus of all of this. Substituting it in, we have dr dt all squared is minus that plus that. And then what we do is we can factorize out the common denominator, 2g m2 minus m1. And what we need to do is just here, notice that this should give us, notice here we get 1 on big R minus 1 on little r. Now we have this very strict condition that dr dt all squared is equal to greater than 0, which means all of this must be equal to or greater than 0. Now there's 3 cases to consider because you've got m2 minus m1. It could be that m2 is bigger than m1, or m2 is less than m1, or the two are equal. So let's start where m2, remember that was our negative mass, is greater than m1. And then we have 1 on big R minus 1 on little r is equal to greater than 0. So 1 on r is equal to greater than 1 on little r. And flipping that around, we get r is equal to or greater, little r is equal to or greater than r. So in this case, where the negative mass is greater in magnitude than the positive mass, then in this case, we clearly have repulsion, because at t equals 0, the particles were at r, and at all times after that, little r is equal to or greater, grows larger than the big R, greater than the r we started with. So we have net repulsion. All right, reminding ourselves again, here's our condition for this being equal to greater than 0. If m2, the negative mass, is less than m1, then what we have is this m2 is less than m1, so this net thing is negative. So if I multiply through by the negative here, they'll swap the position of these two. This becomes plus 1 on r minus 1 on big R. So plus 1 on little r minus 1 on big R is equal to greater than 0. Adding 1 on big R to both sides, 1 on capital R. So r is equal to or less than big R. So in this case, as time goes on, the distance between them decreases from the initial starting value of capital R. So in this case, we have net attraction. Net attraction. And then finally, so interesting, isn't it? So if the negative mass is less in magnitude than the positive mass, we get net attraction. Whereas if m2 is greater than m1, we had repulsion. Now finally, if m2 equals m1, then dr dt is 0. And this condition is met. dr dt is 0. That's equal to or greater than 0, in this case equal to 0. And in this case, the two masses remain the same distance apart. A case of neither attraction nor repulsion. So, not a problem. Interesting. All right, now the case for two negative masses. Remember, motion to the right is positive, so we have negative m1 at x1, negative m2 at coordinate x2, at t equals 0, at that instant in time. The distance between the two is capital R. Okay. Let's set up the equation of motion. Minus m1 here, or both negative here because they're both negative masses. Minus m2, expecting attraction between two particles, as Newton's law of gravity tells us. Put in the negative masses. All right, divide through by m2 here, divide through by m1 there. Again, same thing, same operation. This one's negative, this one's positive. Add the two together, we get a positive result. Look at the difference so that we can go after our condition again to analyze the motion, and we get a positive result here as well. Next step over, the second order differential equation we have is this plus up here, and a suitable antiderivative will be this one here inside the parentheses here with some constant alpha. Let's just check that's the case. Working it through, we end up here, All right, and so that works. So we have dr dt all squared is minus 2g m1 plus m2 all over r plus the constant alpha, and at t equals 0, the first derivative of r is 0, r equals r, so the two particles are placed initially at rest, a distance capital R apart. What happens? All right, well, let's solve for the constant alpha. 0 here on the left is equal to this. Alpha is this object here. Let's put it back in. All right, when we do that, we can factorize out the common numerator here. And that minus there means we have negative 1 on R plus 1 on capital R. So we have this object here is this one. Now, this is always positive. We don't have to worry whether M2 is greater or less than M1 and all the rest of it, we don't have to worry. This thing's positive anyway. For dr dt squared to be equal to greater than 0, we then have 1 on capital R minus 1 on little r is equal to greater than 0. Solving for that, we get this object here. And flipping, now when we flip them over and then we bring the r over here, we find that r is equal to, little r is equal to or greater than capital R. So what we have is net repulsion. So the two particles are placed at a distance capital R from each other, and thereafter, once released, the distance between them will continue to grow. So a case of net repulsion between two negative masses. All right, so in summary, two positive masses, attraction, as in the Newtonian case, a positive mass and a negative mass will give us net acceleration to the left if they're the same mass. Attraction if M2 is much less than M1. For two negative masses, we have net repulsion. Simple case there, net repulsion. So one aspect of negative mass is they would accelerate in the opposite direction to which it was pushed by some force. So if we just look at Newton's second law here, at the moment, if you, with a positive mass, if this were a plus here and not a minus, then when a force is applied to an object of some mass m, it will move in the direction of that force for as long as that force is applied. It will accelerate in the direction of that force for as long as that force is applied. With negative mass, you give it a push, it accelerates in the opposite direction. So in the opposite direction to which it's pushed, as you can see here. It has been proposed as a way of keeping a wormhole open so that it becomes traversable. As you can imagine here, if you look here, positive and negative, there's no repulsion and there's no attraction. They keep the same distance apart. So suitable enough negative mass could be used to keep a wormhole open. And if you can keep the wormhole open, it could become then traversable. Next bit, in the Schwarzschild geometry, a singularity for negative mass occurs at r equals minus 2gm on c squared, which clearly doesn't make much sense. So there is some problems with this negative mass. I mean, an event horizon in a Schwarzschild geometry should occur at plus 2gm on c squared, which it does. But with negative mass, that would have a negative value. So r would be a negative quantity, and which doesn't make sense. Another possible use of negative mass has been the Alcubierre warp drive. Has been calculated to require minus 10 to the 64 kilograms of negative mass matter, to propel a ship across the Milky Way. Milky Way, by the way, has a mass of plus 10 to the 42 kilograms. So you would see here repulsion. The negative mass is far greater than the positive mass. You would see repulsion, and that would help the Alcubierre warp drive move a spaceship across the Milky Way. But that's an awful lot of matter to achieve that goal. An awful lot of negative matter. Whatever negative matter is, and it's never been observed, whatever it is, it's an awful lot of it. Now, both the conservation of momentum and energy laws hold for systems made up of positive and negative masses, so that works. Just one thing now that causes concern about the whole idea of negative mass is that if you looked at the case we saw earlier with the positive mass and the negative mass, you've got this endless acceleration off to the left there, if you remember the diagrams. And so constant acceleration means the velocity and the kinetic energy are constantly increasing, or the speed and the kinetic energy are constantly increasing. How long could that go on for? I mean, you have this runaway effect of endless increase in energy. So that brings some discredit on the idea of negative mass. It causes some problems there. And there is some speculation concerning its use in explaining dark matter and dark energy through the idea of a dark fluid. You can see how positive and negative matter, particularly where you have cases where the negative matter is much greater in mass than the positive matter, you've got a repulsion at work there. Could that be used to explain the role of dark matter and dark energy? Who knows? It's a very, that obviously needs a lot more work. All right, that's it.